Now here the question is, we need to solve this integral, which is this integral from 0 to 1 x to the power alpha minus 1 upon log x dx. Now here limits are constant and there is a parameter alpha. So this integral will be some function of alpha. So we'll write this as some f alpha and it'll be equal to this integral from 0 to 1 x alpha minus 1 upon log x dx. Now we'll differentiate this function with respect to alpha. So we'll write this as f dash alpha, and on the right hand side we'll use Leibniz Integral Rule. So it'll be this integral from 0 to 1 and then partial derivative of this function with respect to alpha. So del by del alpha of x to the power alpha minus 1 upon log x dx. Now this is f dash alpha and it'll be this integral from 0 to 1. Now log x is constant. We are differentiating it partially with respect to alpha. And then what's the derivative of x to the power alpha? Here x is constant and alpha is variable. So it'll be a to the power x, and differentiation of a to the power x is a to the power x log a. So it'll be x to the power alpha log x into dx. Now here log x and log x will cancel. So we can write f dash alpha as this integral from 0 to 1 x to the power alpha dx, and it'll be x to the power alpha plus 1 upon alpha plus 1 from 0 to 1, which is 1 upon alpha plus 1. So we are getting f dash alpha as 1 upon alpha plus 1. Now we have to find the value of f alpha, and we have this differential equation. Now before solving this differential equation, we'll work out its initial value. So we'll find value of this function when the value of alpha is 0. If we put alpha as 0, it'll be this integral from 0 to 1. Now x to the power 0 will be 1, so it'll be 1 minus 1 upon log x dx, and which is nothing but 0. That means we have this initial condition that when alpha is 0, value of this function is 0. Now we'll integrate this function with respect to alpha. So on the left hand side it'll be f alpha, and this one will be log alpha plus 1 plus c. And we also have initial condition. So when alpha is 0, f0 is 0, log 1 is 0 plus c. That means value of c is 0. So value of this integral will be simply log alpha plus 1, which is what we need to prove. Now here the question is, assuming the validity of differentiation under the integral sign, show that this integral from 0 to pi by 2 log 1 plus y sine square x upon sine square x dx is equal to pi under root 1 plus y minus 1. Now here variable of integration is x, and we also have this parameter y. So this entire integral will be a function of y. So we can write this as fy, and it will be equal to this integral from 0 to pi by 2 log 1 plus y sine square x upon sine square x dx. Now we'll differentiate this function and we'll find f dash y. Now since limits are constant, if we have to differentiate this function, we can write this as f dash y equals integral from 0 to pi by 2. Now we are going to differentiate this function partially with respect to y. So it'll be 1 upon 1 plus y sine square x into sine square x upon sine square x dx. Now here sine square and sine square will cancel. Now we'll write this as f dash y equals this integral from 0 to pi by 2, and what we'll do is we'll divide everything with cos square x. So in the numerator we'll have secant square x upon secant square x plus y tan square x. And what we'll also do is we'll write secant square x as 1 plus tan square x. So this f dash y, it will be this integral from 0 to pi by 2 secant square x dx upon 1 plus y tan square x. Now what we'll do is we'll let tan x as t, then we'll have secant square x dx as dt. Now we can write this integral as f dash y at this integral. Now we'll put the limits. When x is 0, tan 0 is 0, so value of t is 0, and at pi by 2, tan pi by 2 is infinite, t will be infinite, then it will be dt upon 1 plus y into t square. Now this is x square plus a square. So we'll use the formula. We'll get this as 1 upon under root 1 plus y into tan inverse under root 1 plus y into t from 0 to infinite. So this f dash y, it will be 1 upon under root 1 plus y, and then if we'll put t as infinite, it will be tan inverse infinite, which is pi by 2 minus tan inverse 0 is 0. So we'll write this as pi by 2 and then 1 plus y to the power minus 1 by 2. Now we'll integrate this function with respect to y. We can write this as fy, and it'll be equal to pi by 2, and then this function will be 1 plus y to the power 1 by 2 upon 1 by 2 plus c. Now here 2 and 2 will cancel. So value of fy, it will be pi into under root of 1 plus y plus c. Now we look at the question again. We are given fy equals log 1 plus y sine square x upon sine square x. If we put y as 0, then here it will be f0, and this integral will be from 0 to pi by 2 and then log 1. Log 1 is 0 into dx, which is 0. So we are getting this condition that when x is 0, value of fx is also 0. So we'll use this condition to find integration constant. So we'll put y as 0, we'll get fy as 0, and it will be pi plus c. So value of c is minus pi. So from here we can say value of this integral will be pi into under root of 1 plus y minus 1, and this is what we need to prove in the question. Value of this integral is pi under root 1 plus y minus 1. Now here the question is, we need to show that this integral from 0 to infinite e to the power x square cos alpha x dx is 1 upon 2 under root pi e to the power minus alpha square by 4. Now what we'll do is, we'll write this integral function as some f alpha, which is this integral from 0 to infinite e to the power minus x square into cos alpha x into dx. I will differentiate this function with respect to alpha. So it will be this integral from 0 to infinite, and if we partially differentiate with respect to alpha, e to the power minus x square will be as it is, and then derivative of cos alpha x will be minus sin alpha x into x dx. So we'll write this f dash alpha as this integral from 0 to infinite. We'll rearrange it a bit. We'll write sin alpha x into, and then minus x into e to the power minus x square dx. Now what we'll also do is, we'll multiply and divide it with 2. Now we'll solve this question using by parts. So we'll take sin alpha x as first function, and we'll take this as second function. The reason we have taken this as second function is, if we take this as t, it will be simply dt. So its integral will be e to the power minus x square. So we can write f dash alpha as 1 by 2. Now sin alpha x as it is, and then it will be e to the power minus x square from 0 to infinite, and then minus 1 by 2 this integral from 0 to infinite. Now derivative of sin alpha x is cos alpha x into alpha, and here it will be e to the power minus x square dx. Now we put the limits here. E to the power minus infinite will be 0, and if we'll put x as 0, sin 0 will be 0. So the value of this part will be simply 0. That means we are left with f dash alpha equals minus alpha upon 2, this integral from 0 to infinite cos alpha x into e to the power minus x square dx. Now this e to the power minus x square cos alpha x dx is nothing but f alpha. So we can write this function as f dash alpha equals minus alpha by 2 into f alpha. We can rearrange this as f dash alpha upon f alpha equals minus alpha by 2. Now we'll integrate it with respect to alpha. So now it'll be log f alpha, then integral of alpha will be alpha square by 2, so it'll be alpha square by 4 plus c. So we can write this as f alpha e to the power minus alpha square by 4 plus c, or we can write this as e to the power minus alpha square by 4 into e to the power c, which is some constant, say a. So we can write this as a into e to the power minus alpha square by 4. Now we need to find the value of a. If for this function we put alpha as 0, we'll get f0 and it'll be this integral from 0 to infinite e to the power minus x square, and then cos 0 will be 1 into dx. Now this integral is nothing but it is half Gaussian integral, and we have discussed this Gaussian integral in one of the previous videos. So here I'll use the result and I'll put the link to that video in the description below. So we know that value of this integral, it will be simply under root of pi by 2. So when the value of alpha is 0, value of this function is under root pi by 2. So it will be f0 and it is equal to a, and this is under root pi by 2. So value of this integral will be under root pi by 2 e to the power minus alpha square by 4, and that is the answer we are looking for.